Hello, everyone. My name is Benda Nandu. If you don't know me, that means you missed the first two parts of this series. So I would highly recommend you go back and look through our YouTube channel so you can make sure you watch parts 1 and 2. Parts 1, we went over what is calculus exactly. Part 2, we talked about what are limits, and we even referenced Mean Girls a little bit. And today we're going to review limits, but then we're also going to go into continuity. So limits and continuity are kind of the quickest parts of calculus, but this is definitely something you want to have a good foundation for moving forward into calculus, because you're going to have to use a lot of these for derivatives and integrals, which is going to be a big part into the next big topic, which will be derivatives, which we'll talk about when we're going to be discussing that. So let's get started. So again, my name is Benda Nandu. We're going to be talking about limits and continuity. I am the Center Director at Mathnasium of Midlothian. For those who do not know what Mathnasium is, we are a math-only learning center, typically catering to children in 1st through 12th grade in our regular program. And then we also help students outside of that. One of my favorite areas to teach is actually calculus, hence why I picked calculus for this webinar series. So like I said, this is part 3. We're going to dive into limits and continuity. So we're going to first review what is a limit. So we went over a lot about limits last week, so I'm not going to spend too much time on it, but I do want to reiterate it for anyone who missed our webinar last week. So first thing, what is a limit? So whenever we can evaluate a function, which sometimes happen in math, I know sometimes you're like, hey, math is supposed to be, we always get the answer and that's it. That's what I like about math myself. But sometimes, you know, just like in life, things aren't that simple. So limits definitely help us understand functions better. But whenever you hear limits, I want you to think about approaching. When we're doing a limit, we're not always trying to find the value of the function that we're looking at that limit for. We want to see what that function is approaching. So we use limits to define continuity, which we'll get into next, as well as derivatives and integrals. So I do want to briefly go over just the nomenclature of limits as we talk about, as in calculus. So if you look at our graphic down here, you want to look at the limit as x approaches a of negative infinity, which means we're approaching it from the left side. This is our left-sided limit. And the limit as x approaches a from positive infinity. This is what I think about the minus and the plus. That means we're approaching from the right side. But what's key is that if the limit from the left and the limit from the right do not equal, then the limit does not exist. But let's talk about evaluating limits, because that's also very important. So I am a very analytical person, so definitely flowcharts are my favorite. So if you look at this flowchart over here on the right side, this definitely gives you a good kind of structure of what you want to do when you're evaluating limits. And I do want to just review some of these things after I go over all of the flowchart. So the first thing you want to think about when evaluating limits is just like how we talked about. Sometimes when we use limits, we can't find out if there's an exact value of the function. Limits can also be used when we do know there's an exact value of the function. So the first thing you always want to do is see if you can just plug it in. If you can plug it in, that's it. That's algebra. You're not even using any calculus there. So that's awesome. But that's not always going to work. So what we want to try, what we want to look at is first, is there going to be a asymptote? So you can see here in part B of our little flow chart, if we have something and it's being divided by 0, that is a domain restrictor. Throw back to algebra 2. Domain restrictor that we can't always fix. So sometimes we don't have a limit there, or we can see what it's approaching, but we know that there's no value. Or we can find the limit because we can plug it straight in, or we can get what's indeterminate form. So there's multiple types of indeterminate form. The main two are 0 over 0, as well as infinity over infinity. Now moving on, say plugging it in doesn't work. The first thing I would suggest for you to do is factor. So typically if you have a rational function, which just means a fraction with variables, see what you can do to factor out the top and factor out the bottom to see what you can reduce and see if anything can cancel. And then like in this example here, when we're factoring x squared minus x minus 2 over x squared minus 2x minus 3, when we factor everything out, something cancels and we're left with x minus 2 over x minus 3. Now we're not getting a 0 in the denominator, so we can evaluate that function by just plugging it in. Next thing is conjugates. Conjugates are when we have rationals and we want to figure out how to cancel them out, or so we can rearrange something so we can not get a 0 at the bottom. So our conjugate here would be the square root of plus 2. We would multiply that in the top and the bottom to get rid of that square root in the top. Now, mind you, if that did not make sense, I don't want to touch too much based on that, but we definitely want to review back in algebra to see what conjugates are. And then as far as like pre-calculus and trig, there are several trig identities you could use, like in this example here, to simplify something to make sure you're able to evaluate your limits. I just wanted to show you guys how we can evaluate some limits. So the first easiest thing we can do is we can try to evaluate just by plugging it in. I know you're probably looking at me like, Benda, how can we find the limit of a constant? A constant meaning something that we don't have a variable with. 5 is always 5. Well, let me tell you, constants are your easiest limits because you don't have to do anything. The answer is 5. So if you look at that graph, which I'm going to show you a crude drawing of, no matter what we put in for x, we always get y out. We always get 5 out for y. So no matter what we're approaching at whatever point, at -1, it's 5. At 0, it's 5. At 1, it's 5. Whatever, it's 5. All right, so let's try and do number 7. All right, we have the limit as x approaches 1 of negative x minus 1 in the top, and then we have x squared minus 6x plus 8. Can someone out there in the crowd tell me, what does negative x minus 4 over x squared minus 6x plus 8, or let's take it in pieces, what is our denominator, x squared minus 6x plus 8 equal after we factor it? This factors into x minus 4 over x minus 2. And let me not forget the negative. So now you're saying, okay, Benda, we have an x minus 4 on the top and an x minus 4 on the bottom. That means something good for us, right? Yes, it does. That means we can just cross it out. Now we have -1 all over x minus 2. So that was, I think, D on our flow chart. We know we couldn't plug it in because when we plug 1 into this, we do get a 0 in the denominator, but we know we could factor it out, and we went ahead and tried that. So now that we have something reduced, now let's see if we can plug it directly in. And last time I checked, 1 minus 2 didn't equal 0. So because of that, our limit does equal 1. Because you plug in 1 minus 2, you get -1. -1 divided by 1 is 1. So that's how you can do a limit. I don't think this worksheet has a lot with trig identities, which is another thing I wanted to show you. One of my favorite resources is CUDA. CUDA is a learning software that typically math teachers use. If you're in the Richmond metro area, you've probably definitely seen some of these worksheets from CUDA. They do offer free worksheets with free answer keys on a variety of topics, everything from pre-algebra up into calculus. So the website's literally cudasoftware.com. And if you hover over this free worksheets, you can see that there's a variety of different maths that they provide. And then this is the calculus page, there's several topics on here with several different worksheets, and all have their own answer keys. So that is a review on limits. Hopefully, if you did miss last webinar, that was a good refresher, but I definitely encourage you guys to look at the last webinar to go more in depth on what limits are and how to evaluate. So now we're going to talk about what is continuity. So continuity is whether the function is continuous at a certain point or not. So right here, I have a statement, and this is something that in calculus, you just got to memorize, but it actually does make sense after we apply it to the graph, which I'll show you. So a function is continuous at a point if and only if f of a is defined, meaning we have an actual numerical value for this point when we plug a, which the function is approaching, into the function. If the limit as x approaches a is defined, and then the third condition is if that limit as x approaches a of f of x equals that value of f of a. So all three of these conditions must apply for you to be able to determine that a function is continuous at this point. And I will say you also do want to go in order, because typically if the first one doesn't work, you don't need to test the second and the third one. If the first one works and the second one doesn't work, don't test the third one. Don't waste your time. Let's talk about that in a graph. All right, so we're going to zoom in on this other beautiful CUDA page. I will also say another thing from Algebra 2 and also trig is that you would definitely want to get in the habit of knowing how to graph linear, parabolas, really just any type of functions that you would typically see, like those parent functions and their transitions, as well as piecewise functions that you can see in number 1. because you will not always be given a graph, and you will not always be given a graphing calculator. So you will have to make your own drawings and make your own assumptions based on those. But on this page, we definitely have a beautiful drawing that we did not have to do. I did not do that myself. So we're looking at a piecewise function f of x. When x is less than 1, the function x squared plus 2x plus 1. And then when the x is greater than or less than 1, our function is negative x over 2. So as we see here, the first part of our function, which x is less than 1, that's our parabola, our quadratic here. And then as x is greater than or equal to 1, notice the closed circle, we have negative x over 2. So over here, we're trying to find the interval where a function is continuous. So first thing is we want to go through our conditions. We want to look to see if in all points, because this does go on infinitely, if at all points that this function is continuous. And what's typically easiest is if you want to find out one point or multiple points where they are discontinuous, and then stating your continuity around that. So I will go back to our first condition. Is there a defined function at every single point on our graph? So we know from negative infinity, blah, 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 blah. And then we get down here, we have all of these solid points here. We don't have any holes. Oh, we have a hole at x equals 1. But do we really? It is an open hole at 4, but we do jump down to negative 1/2. And then we do, that is the value we have when x equals 1. So as we're approaching, we'll go into limits in a second, sorry. But if we're talking about just if there is a function, if there's a defined point at each part of this function, the answer is yes, that fulfills condition number 1. Now going to condition number 2, we're looking at the limit, if the limit has a defined answer. So remember back to last webinar where we talked about limits. If a limit does exist, that means the left-handed limit and the right-handed limit are both equal. So let's look at our left-handed limit. So in our left-handed limit, we are approaching from the left side. And this is if we're approaching 1, since this seems to be the only problem point. If we're approaching x equals 1, we see that y is approaching 4. Now let's look at the right-handed limit. We just talked about how it kind of jumps down, and as we approach from the right side, it approaches negative 1/2. Does 4 equal negative 1/2? Not today, it doesn't, not any day. So we definitely want to make sure that second condition is fulfilled, because in this graph, it does not. So that means that it is not continuous at this point, but we just talked about how it is continuous at every other point. Like I said, every CUDA page has their own answer key. We are continuous from negative infinity. That's what the arrow means. We're just going to go continuous on, and we're talking about domain here, from negative infinity into 1. And then we start at 1 again, and then go to positive infinity. Some of you may be asking me, Benda, why is this one have a parenthesis? And then why does this one have this kid told me it was a half a square the other day. It is definitely a bracket, or a square bracket, if you want to call it that. So Benda, what's the difference? Parentheses mean not inclusive, and brackets mean we are including. So as we are approaching from the left side, as we're approaching x equals 1, we just talked about how y was approaching 4, but there's a hole here. That means it will never actually equal 4. So that is a parenthesis for our domain, but it does jump down to negative 1/2 and then continue on to positive infinity. So that's why we have a bracket, because it includes 1. Also, side note, you will never have a bracket on an infinity. Infinity is just an idea. It is not an actual value that we can set. So there will never be a bracket on infinity. Please, that's like my pet peeve, when people just put brackets everywhere, including on infinities. Please do not do that. That handles continuity there. So hopefully that makes sense about what continuity is, and definitely make sure that you follow up on those 3 conditions to make sure you understand what it all entails to be a continuous function. Now let's briefly talk about number 2 here. We have f of x, where f of x equals 1 when x doesn't equal 5, and then f of x equals 3 when x does equal 5. So as we see here, kind of like what we talked about in that problem earlier, we have a horizontal line where y equals 3, but then at x equals 5, we kind of pop up and go to 3, and then we come immediately back down. So all right, let's see if this is continuous. Condition 1, does f of a or f of 5, since that's the only point we're worried about, have a value? Yes, f of 5 equals 3. It says it in the question. X equals 5, f of x equals 3. Second one, does the limit, the left-handed limit and the right-handed limit equal? Let's look, shall we? So from the left side, we are approaching 1. From the right side, we are approaching 1. The left-handed limit are equal. The right-handed limit is equal to 1. So that means they're both equal. So that satisfies our second condition. So look, we've gotten farther than we did in question 1. So now let's see if the third condition is satisfied. Our third condition is that f of a, or f of 5, is equal to the limit as x approaches 5. Is that true? So we just said f of 5 equals 3. But then we just said the limit as x approaches 5 of f of x equals 1. 1 does not equal 3, so therefore that does not satisfy our third condition. So this function is also discontinuous at x equals 5. So our interval here would be negative infinity from 5, and then from 5 to positive infinity. Please notice there are no brackets here, because as we can see, the parentheses around the 5 show us that it never touches 5, except when we jump up to y equals 3. So just be careful with your parentheses and brackets again. So obviously, if something is continuous, we write an interval for that continuity, or it can just be continuous throughout all real numbers. But then we want to talk about when it's not continuous, it's called discontinuity. And there's 3 main types of discontinuity. There's a fourth one that, to be honest, I've only seen once, but we'll talk about that next. But there's jump, there's removable, and then there's non-removable. So let's go ahead and jump into that, shall we? So let's see, now we're talking about types of discontinuity. So a jump discontinuity is kind of like in that problem we just saw where y equaled 1 for everywhere except where x equals 5. But here we see that from the left side, we're approaching the constant L, but from the right side, we're approaching our constant M. So we see at that one instance where x equals a, that it jumps from L to M. So next, we're going to talk about infinite discontinuities, which are also known as non-removable discontinuities. So infinite discontinuities are when we're looking at vertical asymptotes. So that can mean both of the ends of the function are approaching positive infinity, both of the ends of the function are approaching negative infinity, or one end of the function is approaching negative infinity, the other is approaching positive infinity. Regardless, infinity is not a number, as we discussed. So even though they're approaching the same thing, that does not mean we are continuous, as it shows here. So this one, we're approaching positive infinity, this one, we're approaching negative infinity, and this one, we've got one of each. So now my favorites are the removable discontinuities. So I really like removable discontinuities because that is literally just meaning we can kind of just put something there to make our function continuous. So you would definitely be encountering some questions in calculus to say, okay, our function is discontinuous at this point. What can we do to make it continuous? And sometimes you have to do that, especially as we're trying to find derivatives and integrals of a function. So as you see here on both of these, we have on the left and the right sided limit, we are approaching L, but our actual value is equal to M. So this is where we're talking about that third condition where both our limit and our value have to be equal. This one, we do have a limit that's equal, but our value does not equal anything here. So we want to see, like, what can we do to make that continuous? We could literally, I won't show you how right now, but we can literally just, place a value into that A to make it equal L so we can make the entire function continuous. But then we have another discontinuity where there just is no jump per se. There is just an empty space. So that does not fulfill our first condition. There is no f of a. It's just approaching the same value, but we don't have anything here. There's no, extra dot like we have over here. Oh, endpoint discontinuity is also a good point. So sometimes we're not always finding continuity at all real numbers. Sometimes we're just going to look at if it's continuous at a certain interval. So there's definitely discontinuities when we have a closed interval because we're starting at a certain point. And remember, with continuities, we have to find the left and the right-handed limit. And depending upon what end of the interval we're looking at, if we're starting from a certain place, we can't look at the left side limit because there is no left side limit in this case. Or sometimes we can't look at the right side limit because, we've gone as far right as we can. Now let's talk about mixed discontinuities. Sometimes, probably very rarely, probably never if you're in high school, you'll see where we have an asymptote and we also have a hole. Holes are in a function where if we're looking at rationals, we have a factor that disappears in the top and the bottom because we factored it out. There is a hole at that part. But in here, we have both. Only thing you need to know is discontinuous like everything else. But what I did want to talk to you guys about lastly is the intermediate value theorem, which you will most likely see shortened as just IVT. So the intermediate value theorem tends to be what some people think are common sense. So, sometimes in math, we just want to lay out this law to just make sure everyone understands. Because believe it or not, everyone does not have common sense. Not that you guys don't, I'm sure you do. So let's talk about intermediate value theorem. As we see here, I'm just going to read it verbatim. It says, suppose that f of x is continuous on a closed interval a to b. Side note, notice the brackets, not parentheses. That means we're closing at a and we're closing at b. That's a closed circle. And let m be any number between f of a and f of b. Then there exists a center c such that a is less than c is less than b, and 2, that f of c equals m. So as we look at this diagram, I know that a lot of those words, that just doesn't mean anything to you. As we look at a function, and we know from a to b, we have a y value that's, let's say this is 1, and we have a y value, let's say that the b gets us to 5. We know that if this is a continuous function, this is where continuity comes in. If this is continuous, then we know for a fact somewhere in between when x equals a and x equals b, there is a y value that x can equal 3. Because, we can't just count, if it's continuous, we can't just do 1, 2, 4, 5. We skip 3, right? So there's definitely going to be a point in that series that we know that there's a function there. And what IVT shows us is that sometimes we do want to know if there's a value there, but we don't have to find it. And sometimes it is hard to find it. So we can just use IVT to prove that there is a point in time where we are equal to that function because of the point of where we start and ends. And, if it's continuous, we have to hit that value at some point. Ooh, a tip is that what my calculus teacher in high school used to say, and it always carried with me. When you're drawing a graph, if you have to lift your pencil up even once, that means the function is not continuous. So just knowing that there is no way we can skip over a value in between the closed interval a and b, because that means we'd have to pick our pencil up. So that is a kind of watered down version of those 3 conditions. So just remember that if you see a graph and you just visualize yourself drawing it and you have to pick your pencil up, that does not mean that it's continuous. You definitely want to try your 3 conditions to prove that it is discontinuous. That is the last thing I wanted to share. Calculus does have a lot of theorems, so IVT is typically one of the first ones. Sorry, intermediate value theorem is typically one of the first ones. I would definitely suggest, if you haven't already, diving into the more complex theorems as you get higher into calculus. But I do want to share with you guys, as I close out on limits and continuity, that next week we will be doing part 4 of this series, where we are going to dive into derivatives. And I should say introduction into derivatives. We are not going to do derivatives as a whole, because this is definitely a big topic. But derivatives are definitely, as we're talking about, math builds upon itself. Derivatives is going to give you the nice solid foundation you're going to need for the rest of your calculus. And typically everyone, no matter what calculus you do, you're going to be doing derivatives. So I definitely suggest, and it might even be the end of your calculus class. But with that, I close out. I want to see if we have any questions.
Okay, so I'm going to start you off with 2 that we already have. So the first question is, how is all real numbers notated?
Ooh, so if we want to say x belongs to all real numbers, we can say x, and this is not pretty, belongs to all real numbers. So this is how we notate all real numbers. And this is just saying the instance you're talking about belongs to this range. If we're saying x belongs to, just 0 to 1, we can say this, but you would typically not see that.
Yeah, the all real numbers is just kind of like an R with an extra bar on the end.
Yep.
Okay, and then another question is, what other online resources do you use or recommend?
So, I've been talking nonstop. Definitely CUDA, mainly because it is there's a lot of awesome math resources out there that are free. But the problem with calculus is that it's so high level, tend to be limited resources. So what I typically recommend is Khan Academy if you need to learn calculus. These webinars, because I'm an awesome teacher and I'm here for you weekly. But then also CUDA if you've already learned the topic and you want to practice it. That's one thing about CUDA. This isn't where you want to learn limits so you can just go into CUDA and do a limits page. No, there's no actual instruction going on there. So definitely that's when you've already learned it and you just want to practice it. But those are my two favorites. But there are typically a lot of resources online. One of the websites I will revert back to really quickly, actually from a college, just right here. So there's Dr. Paul, and he's at Lamar College, which should say somewhere. I don't know. But if you look here, he goes into a lot of math classes, but specifically if you go into calculus, he has actual pages where you can actually review with him. There's like his notes that he taught in school. He's retired now, but he was teaching in his classes at Lamar University, I guess, whatever it is. But there's definitely a lot of areas that he touches on. And not only are there instruction pages and notes, but there's also practice problems that also gives you solutions. If I'm not mistaken, yes, the solutions also give you work. So it's not just the answers like CUDA. So I'd also definitely recommend this. And it's just tutorial.math.lamar.edu. And this is kind of old. Like I started looking at this in high school. Yeah, it's like 2003. It looks like it's been updated by Dr. Paul in 2020. But, calculus has not changed that much in the past 400 years. And I don't expect it to change anytime soon. So
I love that YouTube also has a lot of good options for good YouTube channels. I know I used to subscribe to Patrick JMT when I was in college and doing calculus, but I'm certain there's tons more videos out there now than there was when I was there.
Definitely. Goodbye, everyone. Thank you for joining us.
Thank you.
Bye.